Late at night in London in 1812, a 21-year-old blacksmith's son named Michael Faraday desperately bound a 300-page volume of his own handwritten notes. He was mailing it to Britain's top chemist, begging for work, his only escape from a lifetime of manual labor. I'm going to show you how an apprentice who never learned algebra invented the invisible architecture of modern physics, and why the greatest mathematician of his century spent years translating Faraday's pictures into the equations that gave us radio. To understand how a man with no formal education rewired our understanding of the universe, I need to take you back to that bookshop. In 1805, 14-year-old Michael Faraday was apprenticed to a London bookbinder named George Rebow. Surrounded by leather bindings and the smell of hot glue, Faraday didn't just assemble the books, he read them. A popular science book called Conversations on Chemistry became his teacher, and he spent his meager pennies on scrap materials to test its experiments in the back room. By 1812, a customer noticed the boy's brilliance and gave him tickets to 4 public lectures at the Royal Institution, delivered by Humphrey Davy, the most celebrated chemist in Britain. Faraday sat in the audience, making meticulous notes. He illustrated them, bound them into a beautiful 300-page volume, and sent them to Davy, requesting a job in science. Davy replied kindly, but told the boy there was no position available. Then disaster struck the laboratory. Davy was working with nitrogen trichloride, an incredibly volatile compound. It detonated without warning, temporarily blinding him. Unable to read or write, Davy desperately needed an assistant. On March 1, 1813, Michael Faraday walked into the Royal Institution as a chemical assistant. He had his foot in the door, and within a decade, he would build something the greatest scientific minds in Europe had failed to create. In 1820, a Danish physicist named Hans Christian Ørsted noticed something strange. When he placed a compass near a wire carrying an electric current, the needle twitched. This was the first proof that electricity and magnetism were connected, but the needle only twitched and stopped. Humphrey Davy and other elite scientists tried to turn this effect into continuous motion, to make a wheel or a wire spin as long as the current flowed. They all failed. So Faraday tackled the problem himself. In September 1821, he built an elegantly simple device. He placed a permanent bar magnet standing upright in the center of a small pool of liquid mercury. Then, he suspended a copper wire so it could pivot freely, with its lower end dipping into the mercury. He connected the top of the wire and the mercury pool to a battery. When the current flowed, the wire didn't just twitch, it swept around the magnet in a continuous, endless circle. Here is what Faraday realized. Most forces in nature push straight ahead or pull straight back, but a magnetic field is strange. It pushes sideways. While rivals hunted a push or pull, Faraday pictured the magnetism around the wire as geometry in space, circles of force looping around the current, his first glimpse of the invisible architecture he'd later call lines of force. A wire free to follow them never stops. When current flows through a wire, it creates its own magnetic field. But placed inside the field of a permanent magnet, the wire doesn't just pull closer or push away. It experiences what we now call a Lorentz force, a push that is perfectly perpendicular to both the current and the magnet. It gets shoved sideways. Because the wire was dangling in liquid mercury, which conducts electricity but flows like water, the circuit never broke. The sideways push never stopped. This was the first time in history that electrical energy was converted into continuous mechanical motion. Faraday had just built the ancestor of every electric motor on Earth. Faraday's motor caused a sensation, but it also caused a bitter rift. Humphrey Davy felt Faraday hadn't properly credited the earlier failed attempts of his peers, and the resulting friction pushed Faraday away from electricity for years. He spent the 1820s discovering benzene and liquefying gases, but he never stopped thinking about magnets. If electricity could create magnetism, Shouldn't magnetism be able to create electricity? In August 1831, he built a device to test it. He took a thick ring of soft iron and wound two separate electrically insulated coils of copper wire on opposite sides of it. He connected one coil to a battery and the other to a meter. There was no physical wire connecting the two sides. When he ran a steady, continuous current through the first coil, the meter on the second coil read absolutely zero. A stationary magnetic field did nothing. But Faraday noticed something in the exact fraction of a second when he connected the battery. The moment he closed the circuit, the meter kicked. And when he opened the circuit, disconnecting the battery, the meter kicked the other way. It wasn't the presence of a magnetic field that moved the electrons. It was the change in the field. When the battery was connected, the magnetic field in the iron ramped up from 0 to full strength. Like a wave crashing through the iron, that expanding field physically shoved the free electrons in the second wire. Once the field was stable, the pushing stopped. When the battery was disconnected, the field collapsed, and that collapsing wave shoved the electrons in the opposite direction. This is electromagnetic induction. By October of that year, Faraday replaced the iron ring with a copper disc spinning between the poles of a magnet. As the copper spun through the field, it felt a continuous changing flux, producing a steady, continuous current. He had just built the world's first electrical generator. Every power plant on Earth today, whether it burns coal, splits atoms, or catches the wind, runs on this exact principle. They are all just massive machines designed to spin magnets past coils of wire. But Faraday's deepest contribution wasn't a machine, it was a concept. Scatter iron filings over a piece of paper with a bar magnet underneath, and the metal dust snaps into curving arcs, reaching from the North Pole to the South Pole. To the scientific establishment of the 1830s, this was just a neat geometric trick. The reigning dogma of the day was action at a distance, the idea that magnets and charges simply pulled on each other instantly across empty space with nothing between them. Faraday had never learned even basic algebra, let alone the complex calculus his peers used to justify this abstract idea. So he trusted his eyes. He looked at those iron filings and claimed the arcs were real. They were physical entities filling the space around the magnet. He called them lines of force. He argued that where the lines crowd together, the field is strong. Where they spread apart, it is weak. The geometry of the lines dictates the physical attraction. In Faraday's mind, space wasn't empty, it was a physical medium filled with an invisible web of tension and stress. When you push two magnets together, you aren't just moving metal, you are compressing the invisible lines of force between them. He had just invented the concept of the field. But here is the problem. The academic elite dismissed Faraday's lines of force. They saw them as the naive physical crutch of an amateur who didn't understand mathematics. Without equations to back it up, the field concept was treated as a hallucination. But a young Scottish mathematician named James Clerk Maxwell looked at Faraday's work and saw the truth. Maxwell would be remembered as the greatest mathematical physicist of his century, ranked alongside Newton and Einstein. He realized Faraday's mathless picture wasn't a metaphor, it was a physical claim about reality, and Maxwell deliberately set out to translate Faraday's physical lines into rigorous mathematics, a labor that took him a decade from his first paper on Faraday's lines of force in 1855 to his completed theory in 1865. The result was Maxwell's equations, the absolute bedrock of classical electromagnetism. By treating Faraday's fields as real mathematical entities, Maxwell proved that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. They can leapfrog off each other, traveling through empty space as a self-sustaining wave. When Maxwell calculated the speed of that wave, the number perfectly matched the speed of light. Light itself is an electromagnetic wave rippling through Faraday's lines of force. The handoff between the two men is one of the most beautiful exchanges in the history of science.
Maxwell turned the pictures into equations, and Faraday, then in his 60s, wrote back to the young mathematician asking him to translate his results back into common language so the old Bookbinder could understand them. Because of that translation, we have radio, Wi-Fi, and the entire wireless world. Faraday's intuition about fields allowed him to see things no one else could. In 1836, he built a 12-foot wooden room, coated the walls with metal foil, and blasted the entire structure with high voltage from an electrostatic generator. Sparks rained down on the outside, but Faraday stepped inside with sensitive instruments and measured absolutely zero electric field. The free electrons in the metal foil had rearranged themselves to perfectly cancel the external field inside the room. It is the exact reason you were safe inside a metal box during a lightning storm, and the reason a microwave oven door has a metal mesh. We still call it a Faraday cage. But around the age of 48, Faraday's mind began to fail him. He suffered from severe memory loss, giddiness, and confusion. "I cannot spell or write a line continuously," he confessed in a letter. Yet, he kept working. He founded the Royal Institution's annual winter lectures for children, which still run today. In his most famous series, he used a single burning candle to explain the entire physical universe, from the capillary action drawing the wax up the wick, to the oxygen in the air, to the carbon dioxide we exhale. As his fame peaked, the establishment tried to crown him. He was offered the presidency of the Royal Society, the highest scientific office in Britain. He refused, fearing his declining mind couldn't handle the responsibility. Telling a colleague he must remain plain Michael Faraday to the last. He made it known he would refuse a knighthood too. Michael Faraday died at Hampton Court in 1867. Think back to that 21-year-old bookbinder's apprentice, sitting up late by candlelight, desperately binding his notes. He didn't just escape the bookshop. He gave us the electric motor, the generator, and the invisible architecture of every modern field theory. Decades later, Albert Einstein kept 3 portraits on his study wall: Isaac Newton, James Clerk Maxwell, and a blacksmith's son named Michael Faraday. Here's a question for you to debate down in the comments. If Faraday had been formally trained in the rigid mathematics of his day, do you think he would have ever been able to imagine the field? Or would he have been trapped by action at a distance like everyone else? If this video sparked a current in your own mind, hit that subscribe button and leave a like. It helps the channel's algorithm more than you know. This is LynxSifts Tech and Science. Thanks for watching.